Okay, so let's start. Welcome to week 12's problem solving session for competition complexity course. Today we'll first solve last year's week 12 assignment. Then we'll solve this year's week 12 practice assignment. And finally, sorry, and finally we'll solve this year's week 11 assignment. Okay, so let's start with last year's week 12 assignment. The first problem is which of the following is true about the computation capabilities of prover and verifier in the setting of the complexity class IP. The options are the prover and verifier are both all powerful. The prover is all powerful, but the verifier is computationally bounded. The verifier is all powerful, but the prover is computationally bounded. And the prover and verifier are both computationally bounded. The correct answer over here is that the prover is all powerful and the verifier is computationally bounded, as we saw in the class. Note that if the verifier is all powerful, then there is no point of having a prover. The verifier can definitely not be all powerful, and the prover is all powerful because it has to prove something with the verifier. So, for example, if the prover were computationally bounded, then the verifier could do what the prover could do. So there was no point in having a prover. Yeah. So the prover is all powerful and the verifier is computationally bounded. Now let's look at the next problem. And the next problem is which of the following is true of the complexity classes MA and AM? The options are AM and MA are disjoint. Option B is MA is contained in AM. Option C is AM is contained in MA. And option D is AM and MA are disjoint, but neither of them is known to be contained inside the other. So the correct answer to this is MA is contained in AM. And this requires this somewhat long proof. So let's do the proof. Okay, so what happens in MA? So in MA, the prover the verifier decides. So in MA, the prover goes first. The prover is the first person to send the message, and in AM, it's the verifier that sends the first message. AM. Yeah, and this part is crucial that it does not use any extra randomness because otherwise it's easy to see that MA is in AM because what the verifier can do is send a string R. Then once the prover replies with a pi, it can pick another random string R prime, and then simply simulate the MA verifier, right? So the non-triviality of this question is because in yes, the non-triviality of this question is because in AM you cannot use any uh, randomness apart from the randomness that you have already sent. Okay, so now if let me add a page. Now if L exists randomized polynomial equals that so this is what it means for a language L to be in MA, and now we want to show that this also means that L is in AM, right? Yeah, uh, uh, so the first step in this proof, okay, so is to ensure, like increase the gap between these two probabilities. So what we'll do is we'll first show that we can assume without a lot of generality that the verifier V prime, when X is in L, the verifier V prime accepts the proof with 1 minus 1 over 2 to the poly n probability, and it when X is not in L, it accepts with only this probability. Yeah. So let's first do that. And this is very similar to what we have done a lot of times in for like EPP algorithms. So all we have to do is execute. Okay, so normally many times on X and pi. So what's happening is that the prover sends pi, and the verifier v prime. We are going to execute v prime on X and pi repeatedly. So we are not going to ask the prover to send multiple proofs. The prover will send just one proof, but to verify it, we'll use much more randomness. Yeah, so by executing p prime polynomial many times on X and pi with independent random strings, say more than say half of the strings. We can use. Yes, so the proof of this uses chain of form, and it's very similar to the proof of boosting the success probability of a PPP algorithm. So I'm not going to do the calculation, but you can do it on your own. It's exactly the same. Okay, so let me call this new prover prime. So now we have a prover that succeeds with overwhelming probability. And what we are going to now do is, okay, so now both of these probabilities are 1 minus 1 over 2 to the p size of x and 1 over 2 p to size of x. But in order to prove that L is also in AM, we would need something stronger. So we would need that this is not there. So we would need completeness 1. So now we'll show how to go from V double prime to a prover to a verifier with completeness 1. So the claim is this. Yeah. So the proof of this is going to be somewhat like the proof of PPP in P slash poly. So just like in that proof, we are going to define this that either so the V double prime is the one that we obtained over here. It's the verifier that succeeds with verbal improbability. X comma 5 and then it's the randomness is and let R be the uh, Yes, so since P double prime is a polytime machine, the size, like any random string it uses is of polynomial size. So R is going to be something like 0, comma 1 to the q size of x for some polynomial q. But yeah, we don't need to be that explicit. We can just have some R. Yeah. So now there are two cases. So if x is in L, then size of this set is at least 1 minus 1 over 2 to the p size of x times size of R, and if x is not in L, then its size is so yeah, then as in the proof, there exists polynomial. And x is not in L. Let me copy this. Yes, it's x is not in L. This is not going to be R. And in fact, the size of so this will be at most say half times the size of R. Yes, so by picking QX correctly, depending on the size of R, we can ensure that this is at most half times the size of R. But yeah, since the size of R is like 2 to the poly, QX would only be poly. That's fine. So I won't work like through how to do this because this argument is exactly the same as the one in the proof of BPP in P slash poly. So but now let's see that once we have this, how can we use this to get complete, like one completeness? The page here. So okay, so far our prover was sending pi, but since prover is all powerful, it can compute u1 to q size of x and send it along with the proof, right? And then what the verifier can do is just verify whether this is true or not. So if this is true, then the verifier knows that x is in L. This is not true, the verifier knows it's not in X here. So that's what we are going to do. This is also similar to what was happening in that proof. Yeah, but over there we were guessing u1 to uq size of x using the there exists quantifier. Here, instead of using the there exists quantifier, we are using the prover. minus pi along with u1 to q size of x. And the verifier has to verify that this happens, right? And this verification is also going to be the same as it was in the proof of PPPNP slash poly. So consider the verifier, which fix are uniformly at random. There are too many R's. Are uniformly at random from R and runs p double prime x comma pi prime, or rather x comma pi. It can easily extract pi from pi prime with randomness as R u1. Oh, I forgot to define this. Yeah, so this set is just x is already used. So yeah. Yeah, so now the verifier wants to verify that this is this. And one way to do it is, uh, okay, so if this were true, and no matter which random string the verifier were to pick, that random string should be in this set, right? In other words, there must exist a UI such that uh, for some y in Sx comma pi, y XOR ui is equal to r, which is the same as r XOR ui is equal to y in Sx comma pi. So this is exactly what we are going to do. Yeah, and accepts one of them accepts. So notice that if v double prime accepts one of x comma prime on one of these, that means that at least one of this is in the set Sx comma pi, and that is exactly what we wanted to check, right? So doing this suffices. So we have that x is in L implies probability there exists I such that, okay, yeah, there exists I such that this is in. So this probability is 1, which implies that probability V accepts, oh, I'm calling this V triple prime. V triple prime accepts x comma pi prime is 1, and x not in L implies that probability, it's the same thing, let me just copy. Yeah, this is at most half, which means V double prime accepts with probably at most half. So now we have almost proved the claim. So yeah, the claim was this. Uh, it accepts with probability 1 and rejects it if X is in L and if X is not in L, accepts with probability this. We almost proved this, it's just that this is half. So this is upper bounded by half. Yeah, now we just want to make this smaller, right? So one way to do it is just, yeah, consider a executes. It's just repetition. And it's here we have just one-sided error. So yeah, it's like the boosting of RP or co-RP. So consider a verifier V that executes V double prime on polynomial many independent random string R, then we can show that. No, it's almost the same as this. Let me yeah, show that X in M implies yeah, the completeness does not change at all. So this is one and this is yeah, and this is exactly the claim what we wanted to prove. So the proof of the claim just relies on it's almost the same as the proof of BPP in P slash poly, but instead of using the there exists quantifier, we are now using a prover, and then we have to boost a bit, which is the same as the boosting that we do for R. Okay, so now that we have the claim, let's see how to use it to prove that M is contained in AM. So, uh, so what happens in MA is that the prover goes first, and in AM, the verifier goes first. So now what we want to show is if we have a proof system that the verifier goes last, basically what we want to show is we can switch the order of the message as the prover and the verifier without causing any issues. Yeah, and the claim will help us in doing that. So at the length of pi prime be s size of x for some polynomial. Yeah, this is because like p is still a polytype. So I did not explicitly prove in the proof in this proof that v is polytype, but v double prime, v triple prime was polytype, and v is only executing v triple prime polynomially many times, so it's also polytype. So S is polytype. Now all we need to do is pick a P such that so over here in the proof we had a polynomial P, right? And we did not say what P was. So we can pick P to be any polynomial function. And now what we are going to do is we are going to pick P such that P size of X is greater than or equals to, I think 2 should work. Yeah, but if it doesn't, I will change the constant. Yeah, 2 times the size of X. Yeah. And so now we wanted to switch the like the order of the message is sent by VNP, right? So R first, and then he will reply with. And now we supposed to verify using just R as randomness. It cannot use extra randomness. So now, okay, so if X is in L, nothing changes, right? Uh, Probability that Px comma pi prime is equal to 1. This still remains 1. But the issue is with soundness. So what can happen is this. So now even before replying with the proof pi, the prover sees R, right? So what it can do is now maybe depending on R, reply with different proofs. So in the MA proof or in the MA protocol, the proof pi prime was always the same, right? Regardless of which R the verifier chooses. But now since the verifier has already told R to the prover before prover replies with pi prime, the prover can change pi prime depending on R to increase its probability of convincing the verifier that X is in L, right? Even though X is not. But the above claim will help us in getting around that problem. So, and yeah, so this is at most okay. So for one pi prime, the number of such R was at most this, right? So for all pi primes, it's the number of pi primes divided by 2 to the p. Yeah, so this is this union bound, right? Times the size of all the times size of all random strings. So uh, let me just define this over here quickly. Mm, yeah, and this is so the size of pi prime is at most s. So this is 2 to the s size of x divided by 2 to the. And because of the way we chose s, this is this is equality. So probability that this is upper bounded by. Yeah, and so even if we change the order of the messages sent by the prover and the verifier, the, if X is not in L, then the prover is not able to convince the verifier with a large probability And so, yeah, the soundness, so basically the soundness is also holds, the completeness also holds. And so this is a valid AM protocol. Yeah, so because of this, we can say that if uh, we can say that if L is in MA, that's that then L is also in AM, and so MA is a subset of AM. For so that already proves that A and D are wrong. And about C, so right now we don't know if AM is contained in MA or not, but it is believed that AM is equals to NP, and it's easy to see that NP is contained in MA and MA is contained in AM, and we already know that NP is going to be equals to AM unless the polynomial hierarchy collapses. So unless the polynomial hierarchy collapses, this is also true. But right now we don't we don't have a proof of this. Okay, so yeah, the only correct eh, like as per our current understanding, the only correct answer is MA is contained in AM. Yeah. So this was a long proof. So I hope you understood it. So if you have any questions about the proof, you can ask me now before we move on to the next problem. Yeah, I think this was one of the most involved proofs we saw in all the sessions. Okay, so if there are no other questions, let's look at the next problem. So next problem is, for which of the following values of k can we say that AMK equals to AM? So AMK is a class of all languages which are decided by public or interactive proofs with k rounds. Select all the correct answers. 2, 3, 100, n where n is the input length, and poly n, a polynomial in the input length n. So which of these is correct, or which of these are correct? Okay, so what we know is this: for any constant k, so k is constant and independent of n, the input length. AM k plus 2 is contained in AMK. Now, obviously, AMK is contained in AMK plus 2, so actually this is an equality. And so we have that AM equals to AM is AM2. So this is AM2. So we have that this is equals to AM4 equals to AM6 and so on, right? So what any constant, AMK is just going to be the same as AM. And in among the options, the constants are 2, 3, and 100. So n is not a constant because n depends on the input length n. And poly n is also not a constant because it also depends on n. So the only correct answers are 2, 3, and 100. Is this fine? Okay, so this is fine. Let's look at the next problem. So the next problem is to show that IP equals to P space, we have to show an interactive proof system for which of the following? Number one, 3 SAT. Number two, SAT. Number three, TCP theorem. And number four, TQBS. So which of these is correct? Okay, so in the class we showed that Sharpie was in IP by constructing an interactive proof for the language sharp reset, right, which is complete for Sharpie. Similarly, to show that IP equals P space, we need to construct an interactive protocol for an interactive proof for P space complete language, and the only P space complete language over here is TQBF. Yes, so the answer is TQBF. And this protocol, this interactive proof also uses the sum check protocol. So its idea is almost the same as the proof that SHA-3 set as an interactive protocol. but you need to do some extra things. Yeah. So it's mostly like that, but with some additional ideas. So the answer is TQB. Okay, so now let's look at the next problem. So the next problem is, so these are from this year's week 12 practice assignment. And the problem is, consider the class of languages for which we have interactive proofs with perfect completeness. So completeness is one. Just call this class IP, IP prime, and which of the following is true? IP is not contained in IP prime. IP prime is not contained in IP. IP and IP prime are the same, and IP and IP prime are disjoint. So, which of this is correct? Okay, so first of all, it's clear that this can't be true because so IP prime is a set of all languages which are accepted by proofs with completeness one, right? But if you have a proof with complete, yeah, the answer is C. Yes, they are the same. Yeah. So as I was saying, like IP prime is definitely going to be contained in IP because if you can uh, accept something with completeness one, you can also accept the same thing with completeness two or three, right? The non-trivial part is IP prime contained in IP. I won't show you the entire proof because the entire proof involves like looking at the interactive proof for TQBF. Okay. Yeah. But what I'll do is I'll just like give a very brief sketch telling you why this is. Okay. So, so we know that P space, okay, to show the IP is contained in IP prime, it suffices to show a P space is in IP prime. And so the proof of this uses a sum check protocol just like the proof that SHA-3SAT has an interactive proof. So the proof uses a sum check protocol. For TQBF. So I won't uh, like describe the entire sum check protocol, but what I'll do is I'll just observe that almost any sum check protocol has some properties, and using just these properties, you can prove that TQBF has a interactive proof with completeness one. So what's the general strategy of a sum check protocol? It's this, right? So the prover wants to prove uh, okay, the prover wants to prove a sum claim. Polynomial f x1 to xn. So in particular, it wants to prove something like, okay, the summation of f over 0 comma 1 to the n is some value alpha or something like that, right? And what the prover does is the following. So in every round I, the prover sends a polynomial fi in just one variable. Let me call that variable xj, and the verifier performs some check using some random RG. The point is that if the claim is true, then this check is always going to pass. So yeah, that's a key observation. So the sum check protocol has complete a perfect completeness. Yeah, so this was the overall idea. Now let me just quickly illustrate this idea with the sum check protocol that we already saw in class. So in the class, we saw that way to prove that sharp phi for some Boolean formula phi equals to alpha, uh, it suffices to show that so let's say phi is in n variables. So then, yeah, some phi 1 to n, some pin 0 comma 1, f of p1 to pn is alpha for some polynomial. And what was happening in the sum check protocol? So in the sum check protocol, let's say in the ith round, uh, I'll just do this for the first round. The rest rounds are similar. In the first round, the prover sends, which is supposed to be it's exactly this, but with just two ends. I'll just copy it. So it's exactly this, but now the sum is from 2 to n. And here you have the verifier checks g of 0 plus g of 1 is equal to alpha. and asks the prover to prove that g of r equals to for B2. So now the point is, so if uh, sharp phi is alpha, then this is true. And so what the verifier can do, what the prover can do in the first round is send this polynomial as g, right? Then this will be true. And since g and this are the same polynomial for any value of r, these two quantities would exactly be the same, right? So no matter which r you pick, the prover would be able to convince you that this is true. And so the completeness is one. And like, okay, so there are there are like, so this happens in every round. In every round, the prover always succeeds. So the completeness is one. Now, while the Soundcheck protocol for TQBF is not exactly like this, it's very similar. And so, like what we saw over here also holds over there. So even that Soundcheck protocol has completeness one. And yeah, so IP and IP prime are exactly the same. Is this fine? Yes, if this is fine, then let's look at the next problem. Yes, the next problem is if GNI was shown to be NP complete, then which of the following statements will be true? P equals NP, P not equals NP, P equals BPP, and PH collapses to sigma 2. So which of these is correct? Yeah, so the answer is D. And okay, so the proof of this is like very long. So I won't do the entire proof, but I'll just again give you a sketch of like what steps go into proving it, how you can execute every step. So the sketch is this. Okay, so you first define this class np slash poly, Cn takes n plus pn inputs for some poly. And x in L if and only if there exists a W in 0, 1. Yeah, so this class is almost like NP, but in NP you had a Turing machine that verified whether X was in that verified whether X was in L or not using the witness. Now instead of a Turing machine, you have a circuit family that does it. So this is sort of the as P slash poly is a non-uniform version of P, NP slash poly is a non-uniform version of NP. Okay, and so now if GNI is co-NP complete, So this implies okay, so GNI is co-NP complete, and we already know that GNI is an AM, right? So I think in class you would have seen a public called interactive proof for graph non-isomorphism. So these two together give us that G. Okay, so since GNI is co-NP complete, every problem in co-NP complete reduces to it, and then using the interactive proof for GNI, we can also give an interactive proof for every problem in co-NP. So this means that entire co-NP is contained in AM. In particular, three-side complement is contained in AM, right? So, okay, now it is known that a problem A is in AM if and only if A randomly reduces to 3 star. And what do I mean by random reduction? So this is almost like the a polytime cap reduction, but now the function that computes the reduction is itself random. So there exists a polytime randomized Turing machine P such that X is in L implies, sorry, X is in A implies that probability P of X is in 3 star is at least 1 over the P size. Oh, I forgot a 1 minus. Yeah. And X dot in A implies I've already defined. Okay, I need another. So I've already used P above, so I need another polynomial Q over here. So Q over here is some polynomial. Yeah, and this is not too difficult to prove. Yeah, so I'll skip this. So in particular, almost from the definition of AM, you can see that this is true if I were to replace these by 2 over 3 and 1 over 3. And then all you have to do is boost it. Yeah. So I won't prove this, but this is not too difficult to show. So, okay, we have this. And we also know that 3 stat is in NP, which is in NP slash pool. Yeah, because if you have a Turing machine that verifies it, all you have to do is convert that Turing machine into a family of circuits using ideas similar to those using the proof of Cook-Levin theorem, and you get a circuit family that verifies 3 stat. Yeah. So 3 sat in NP, 3 sat is in NP slash poly, and now we're using that PPP is in P slash poly. We can show that. Okay, so you can think of this as just a non-deterministic version of this. Okay, and this uses the proof is almost the same. Yeah. I think you just, yeah, it's almost the same. And okay, so we can show that AM is an NP slash poly. And since uh, three set complement is in, yeah, so, okay, since okay, so co-NP is in AM, and so this means that co-NP, in particular three set complement, is in NP slash poly. Okay, so we have that co-NP is contained in NP slash poly, and then again, using ideas similar to, sorry, NP, yeah, pH is equal to sigma 2. We can show that pH is, yeah. So basically, the proof of this involves this observation, uh, and then ideas similar to the proofs of PPP in P slash poly and co like NP in P slash poly implies pH collapses. That's why I won't go into details because yeah, it is a long and tedious, but yeah, using the sketch you can work it out on your own. So is this fine? Yeah. So then let's look at the next problem. So yeah, that was all for week 12's content. So now let's look at this year's week 11 assignment. We have enough time, so I can just solve all of them in order. So the first problem is let MF be the communication matrix of a function f from 0, comma 1 to the n cross 0, comma 1 to the n to 0, comma 1. If any partition of MF requires at least n monochromatic rectangles, then which of the following is or are true and select all the correct options. DF is in omega log n. DF is in order 1. The number of leaves in any protocol tree of F is at least n, and there is a protocol tree of F with at most log n leaves. So which of these is correct? Which of these are correct? Yeah, A and C are correct. Yes. So yeah. Okay. So let chi n be the number of monochromatic rectangles. Then we know that deterministic communication complexity of F is omega of log of chi n. So over here, chi n is n, so it's omega log n. So that's why A is correct. And the number of leaves. Yes, over here it's absolute. There is no order rotation over here. So yeah, C is also correct. Yeah, so this is fine. So if this is fine, then let's look at the next problem. So next problem is in the two-party communication complexity model, each leaf in the protocol tree always corresponds to what in the communication matrix? A monochromatic rectangle, a union of combinatorial rectangles, a particular entry in the matrix, and the diagonal entries of the matrix. So which of these is correct? Yeah, it's a monochromatic rectangle. Like this is why this statement is true. Yeah, since like every leaf corresponds to monochromatic rectangles, the number of leaves is at least the number of monochromatic rectangles in a partition. Okay, so now let's look at the next problem. So the next problem is consider the function f from 0, comma 1 to the n cross 0, comma 1 to the n to 0, comma 1. Fx, comma y equals to 1 if and only if there exists some index I for which xi equals to yi equals 1. So what is df? The deterministic communication complexity of f. Order 1, order log n but not order 1, order log square n but not order log n, and order n but not order log square n. So which of these is correct? Yeah, so D is correct. And proof is relatively straightforward. So uh, for a function f, define g to be yes for every x comma y, gx y is the complement of fxy. So in particular, g is also a function like this. Okay, so now g x comma y equals 1 if and only if for all I. So in our case, for the function f that we have, this is 1 if and only for all I, xi is not equals to yi, right? Hence, for us, g is the disjoint function. Okay, so and what do we know about a disjoint function? We know that its communication complexity is omega n, right? So now what we're going to do is we are going to show that if you have a protocol for G, you can use it to consider a protocol for disjointness, the disjoint function. That would mean that the communication complexity of G must be omega n, must be at least as large as the communication complexity of disjoint. Okay, so given a uh, protocol for computing mm, G, we can compute by using the same protocol. But flipping the value at the very end. Yeah, so given a protocol for F, we can compute G using the same communication complexity. And so the communication complexity of G, wait, no, so the communication complexity of F is at least, okay, no, wait. So I have protocol for F. I got a protocol for G using that. Yeah. So the communication protocol, okay, so I should do it like this. So the communication complexity of G is at most the communication complexity for F. Why? Because I have a protocol for G which uses BDF many bits, but I can have a better protocol, right? In fact, this is an equality because G and F are interchangeable over here, right? So G is a complement of F, so F is a complement of G, and so the same thing also holds for F, right? So in fact, using the same argument, and now is equal to omega n, and so P of F is like omega. Yeah, so it's On but not On log n square. And so, what is the proof? So, like in class, did you see a proof for this? Should I give a proof for this? Okay, so if you
A
haven't seen,
theorem was given that
okay,
disjoint of n is at least n.
yeah, but so did you see a proof for that theorem?
I don't think a proof was given explicitly.
Okay, so I can prove it, yeah. So, what's the number? I think it should be English 110. Yeah, okay, so proof is by the Fooling set method.
Yeah, the Fooling set argument was given. I remember.
Okay, yeah.
Yes,
So, okay,
yes.
that, in that case, let me just write the Fooling set and I'm done.
Sure.
So, I won't prove that it's a Fooling set, but uh, x comma x complement such that of size 2 to the n. Yeah, and since we have a Fooling set of size 2 to the n, the deterministic communication complexity is going to be like log of this, at least log of this, so that's n. And the reason that this is a Fooling set is that, okay, for every pair in the set, disjoint x comma x complement is 0. But if you take any y, which is not the same as x, then it like either x must contain so either there must exist in I so that xi is 1 and, and yi is 1. Sorry, and y complement I is 1, or x complement I is 1 and yi is 1. Yeah, so this is a full set. And yeah, so this communication complexity is at least n, and so f is at least n. So the answer is B. Yeah. And let's look at the next problem.
I have
Yeah,
proofs. Like in for disjoint, we saw that a lower bound of n exists. Like
right.
the complexity is at least n, right?
Yes.
And same was shown for the equality problem. the
Okay.
complexity is at least like n, the communication
Hmm.
complexity. So why can't we show that it is exactly n plus 1?
Okay, so I think you so okay, I don't know whether you can show it using the Fooling set method or not, but I think using monochromatic rectangles you can, I think, do it. So for equality, how many rectangles do you have? So you have one for x comma x, and so you have like n rectangles for one each for x comma x, and then you also have one for like x comma y, where x and y are different. So over there you can show that it's n for equality it's n plus one using monochromatic rectangles. Oh, I lost connection. Yes, I lost connection for a while. Can you hear me?
Yes, yes, I can hear you now.
Yeah, and can you see my screen?
Sorry, yes, no, I can't see your screen, but I can see your video.
Okay, so yeah, let me. So can you see my screen now?
Yes, yes.
Yeah. Okay. Yeah. So for equality, so what I was saying is for equality, you can show that you need exactly n plus one bits by using the monochromatic rectangles method. The way you do it is the following. So the monochromatic rectangles are this. So I'm just calling EQ.
Like I meant to say, like, can't we argue that for just comparison we need like n rounds, and to propagate the answer from one side to the other we need an additional bit,
Yes, but that's just one protocol, right? For example, consider parity.
right?
You could have said the same thing, right? I need to send the entire string to the other party needs to send the answer, right? But in that case, you can do something better. So, what you want to argue over here is that no matter how you communicate, you can't do it, right? So,
Yes,
what
yes.
you are showing is that is that just one protocol won't work, right? You need to show that all protocols won't work,
Okay, so what I mean that we have shown a lower bound of n and an upper
right?
bound of n plus 1.
Yes,
So we know that equality must be solved in either n, like n rounds, or n plus 1 rounds of communication,
yes.
like sending other bit. So what, uh, like everywhere we have shown that it can be n or n plus 1. So why can't we like stick, matlab, reduce it to either one of them?
Oh, yes. What I'm saying is you can prove that it requires n plus one bits. I think using the following monochromatic rectangle. So 0 to the end. Okay, so basically, yeah. X comma x for all x in and right. Okay, so I need to do this properly over here. X comma y. No, no, okay, wait. This won't work because yeah, I can switch. Yeah, this is not a rectangle. That's an issue. So I think there is a way to do this using monochromatic rectangles, but I can get n rectangles easily. I can't figure out the last one. Yeah, I think this one. Do I need x or x prime? Okay, so 0x and let me just first write 1y, see what happens. So you have 0x and 1y. Now, if I, so you have 0x, 1y, you have a 0x, 1y, 0x prime, 1y prime. So this is 0. 0x, 1y prime is also 0, and 0x prime, 1y is also 0. Yeah, so I think this should work. Yeah, so I think using, okay, so I think, see, this is also a monoclimatic rectangle, and using these, okay, so wait, but, no, 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 okay, I messed this up. No, this has, no, wait, not these. Okay, so, yeah, right now I can't figure out what the monoclimatic rectangles required for that, but I think you can do it using monoclimatic rectangles.
Okay, so
Yeah.
like, is there some reference for it so I could look at it?
So I think it should be there in Aurora Barak, not sure. Or the worst case is it might be as an exercise in Aurora Barak. Yeah. Okay, so yeah, if this is fine, let's look at the next problem. So the next problem is, given a graph G on n vertices, the function match n outputs 1 if and only if there exists a perfect matching in G. And according to Rath-Wigderson theorem, the deterministic combination complexity of match n is at least which of the following: omega 1, omega log n, omega n, or omega n squares. Which of these is correct? Yeah, it's omega n. Yes, now let's look at the next problem. So next problem is, let EQ be the equality function and EQx comma y is 1 if and only if x equals to y. So which of the following sets is or are a Pooling set for EQ? And select all the Pooling sets. The options are x comma y where x and y are in 0 comma 1 to the n and both are equal. X comma y where both are not equal. Uh, x comma y where x is 0 to the n and y is 0 comma 1 to the n. Y is anything in 0 comma 1 to the n. And 0 comma n comma 0 comma n and 1 comma n comma 1 comma n. So which of these are Pooling sets? Yeah, so D is correct. D is there. Yeah. A is also true, yes. So yeah, A and D are both. So let's see. Phi. Okay, so for all x comma y and I'll just call the sets S. Uh, equality of x comma y equals to 1 because both are the same. For any x comma y not in S, x is not equals to y, right? So, okay, so for any x comma y, x prime comma y prime in S, okay, so that these two are not equal. Uh, okay, so okay, so x and y are same. So we must have the equality of this is 0. And so, yeah, so A is a full set. What about B is false. And this is because, okay, so for all x comma y in S, EQ of x comma y is 0. So the first condition is satisfied, but for 0 to the n, for 0, 1 to the n minus 1 to the n, and hmm, this, uh, let's say 0 to the n, 1, 0 to the n minus 1. Yeah. So EQ of 0 to the, so both of these are not equal, both of these are in S, and equality of, so this is 0, and equality of 1 to the n, 0 to the n is also 0. Yeah. So this is not a full set. So C is false because 0 to the n comma 0 to the n and 0 to the n comma 1 to the n are both in S, and equality of 0 to the n, 0 to the n is equal to, sorry, 1, and equality of 0 to the n comma 1 to the n equals to 0. Yeah, so set C does not even satisfy the first condition, and D is true because 1. And now the only pair xy, comma x prime, y prime pair is 0 to the n, 0, 1 to the n. So equality of, yeah. So is this fine? Yes, then let's look at the next problem. So the next problem is given a function f x comma y at mf with a communication matrix of f. Suppose rank of mf is 2 to the n, then the deterministic communication complexity of f is at least what? Log 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 n, log log n, log n, or n. So which of these is correct? Yeah, it's D. So yeah, so yeah, so we know this, that the deterministic communication complexity is the log of the rank of M of f at least. And since the rank is 2 to the n, uh, log of rank is at least n, and so yeah, df is at least n. Now let's look at the subjective problems. So the first problem is consider the problem of computing the function average x1, x2 to xn, y1, y2 to yn, where the output is the average of all the 2n numbers. Also for all I, xi and y are like xi and y are poly, like their values are at most poly n. So if Alice has x1 to xn and Bob has y1 to yn, give a deterministic communication protocol for computing average using ordered log n bits. Okay, so here's one way to do it. So Alice computes, so, okay, A defined as sends it to Bob. Bob computes. Okay, and once both of them have this, both of them compute A plus B over 2n, which is x1 plus xn plus y1 plus, which is the average of. Yes, this protocol is correct. Now we need to show that the communication complexity is order log n. So is like order poly n. So sum over I is less than or equals to sum over I in 1 to n order poly. And this is n times order poly n, which is still poly n. Similarly, uh, okay. Yeah, so A and B are both order poly n, and using order log n bits. So the communication complexity is order. Yeah. So is this fine? Yes, this is fine. Let's look at the last problem. So last problem is given the function parity from 0, comma 1 to the n cross 0, comma 1 to the n to 0, comma 1, at the inputs px, comma y in 0, comma 1 to the n. The function parity is 1 if and only the total number of ones in x and y is odd. So give a two-party deterministic communication protocol to compute parity using only constant number of bits. So one way to do it is this. Alice computes and then both of them compute. So now the communication complexity is, yeah, so L is just sent, so the XOR of X1 to Xn is 1 bit. Similarly, XOR of Y1 to Yn is 1 bit, so the communication complexity is just 2. And now this protocol is correct because parity of X1 to Xn, uh, yeah, so this is just XOR of X1 to, and this is the XOR. Yeah, so the protocol is also correct, as in it computes parity correctly. So yeah, we only need 2 bits to compute parity. Yes, so these are all the problems that I have for today. So if there are no other questions, let's end early today. And I think there would be one more session of 1 hour on, I think, this Thursday to cover week 12 assignment of this year. So if there are no other questions, we can end the meeting today early.
I had just one question.
Yeah.
Like regarding the communication complexity problems we have seen, so
Hmm.
the parties have individually too much computational power. So the problem itself is of no consequence. Thing is what information we need to propagate both sides, right?
Right.
So like isn't it possible that if we take a certain tough problem and divide it into two parts, so
Hmm.
the complexity would be like not reducible from n plus 1, like the worst case is n plus 1, right?
Yes.
So like are there separation of classes in this situation, that there are some problems which need exactly n plus 1 and can't be solved in less number of bits?
Yeah. So I think there are there. Yeah. And okay, so we saw a lot of problems that require order n bits.
Right.
I think there are also problems which require order n plus 1 bits. And over here, like you also have notions of P and NP. And also
Within
like,
this
yeah,
setting.
right. So like those classes are called, okay, let me write it. Those classes are called P communication complexity, NP communication complexity, RP communication complexity. But instead of, so for example, in P communication complexity, instead of like requiring a protocol which communicates order n bits, you require the protocol to communicate only like order log n bits or something like that.
Okay.
Yeah.
So it's like sublinear instead of like
Sublog, it's like logarithmic.
oh yes, sir, logarithm.
Yeah. So it makes sense, right? So for example, like we can solve NP complete problems in exponential time, but we don't hope to solve in polynomial time, right? So similarly over here, like you can solve any function in order n times, so let's put it at order log n.
Okay. And
Yeah.
just one more thing, like regarding non-determinism and randomization, like we explored non-deterministic protocols a lot in earlier lectures, like NP class and so on.
Okay.
So, like, is it implementable in real life? Like, does there non-deterministic Turing machine or something like that exists?
Okay. So not unless our world is not deterministic.
Okay. So,
Yeah.
like, is randomization one way to implement that non-determinism? Like,
Okay. So
what?
randomization and non-determinism are different in the following sense. So suppose you have a non-deterministic Turing machine. At every step, it chooses arbitrarily between two transition functions, delta 0 and delta 1, right?
Yes.
So it makes an arbitrary choice. On the other hand, a randomized Turing machine makes a random choice. And the difference between an arbitrary choice and a random choice is the following. So when I say that choose arbitrarily between 0 and 1, you can do anything. But when I say choose randomly between 0 and 1, with probability half you have to choose 0 and probability half you have to choose 1. So for example, if I were to perform an arbitrary experiment a lot of times, there would be no statistics, right? So let's say I were to perform an arbitrary experiment poly n times. You can't say that, okay, n1 many times you would have picked 0 and n1 many times you would have picked 1. But if you were to perform a random experiment poly n times, you can say that, okay, you would have picked 0 with, you would have picked 0 roughly half of the times and you would have picked 1 roughly half the time. So yeah, like random, arbitrary and random are two different things. Arbitrary is much more, because like you can think of a random choice as a subset of okay, a random choice is a weaker than an arbitrary choice. So when I allow you to make a random choice, I give you less power than when I allow you to make an arbitrary choice.
So can I
So,
view it in this way? Like suppose we have a computation tree for a particular
so I
score.
lost you. Can you repeat it?
Like with the like going with the same non-determinism and randomness, like
Right.
let's like we have a suppose a computation tree for certain problem where some of
Okay.
the leaves go to accept and some reject, right?
Right.
So if I have not the power of non-determinism, even if one of the leaf would be like accept
Right.
stage, it would like find the path to it without
Magically. Yes.
without absolute certainty, right?
Right.
But with randomness, we have that with some probability, it is possible that if there exists a leaf which goes to the accept stage, we would find it.
Right. Yeah.
Like we may not have non-determinism, but we
Right.
have randomness. We maybe like we try to we do have various random processes, right? We try to do things randomly in various
Mm.
protocols and all. So like there it with some amount of error we try to compensate the power of like exactly you said that randomness is weaker than non-determinism.
Yes.
So are there another other different ways we try to compensate the power we get from non-determinism? Like randomness I think is one way.
Okay. Another way is like using quantum computers.
Okay.
Yeah. So like quantum computers also do things randomly in some sense, but okay. So right now what we have is this.
So like I know just a little bit about of that. So what I know that instead of being like we are able to say that a bit is just two values and a qubit stores like all the values, a superposition of values from 0 and
Right.
1,
Yeah.
right? So
Yeah. So
like
yeah. So we have BPPs and BQP. So like, okay, so you can think of it like this, like classical randomness, then you have quantum computers, and then you have non-determinism. So it's like this hierarchy.
okay, so is this
Yeah.
hierarchy established?
Okay, so we know this that BPP is in BQP. We do not know if BQP is in NP or not. So this we do not know, but we believe that this is strict. So we believe that this is strict. Yeah.
Okay, so but in our earlier weeks once we had discussed that we know nothing about BPP and NP.
Yeah, yeah. So this is the question mark over here. So, okay, so this notation means that we do not know whether this is true or
Right.
not.
So BQP
Yeah.
sits exactly between those two question mark areas, right?
Okay, so we believe that this is strict, and we also believe that, okay, so these two are not equal. Okay, so what we believe is this. So what I don't know is that do we believe whether BQP is strictly contained in NP or not?
Okay,
Yeah.
so it might be anyway like there. BQP
Yes.
might be more like a bigger class. May it may contain NP or NP may
No,
contain
no. Okay, so
BQP.
we We don't believe that DQT contains NP.
Okay.
So, okay, we don't believe that CSAT is in DQT. So, but what this means that we don't know whether every problem in DQT is in NP.
Okay.
Yeah.
Or anything, any other, like other than quantum?
Okay. I don't think
Uh,
we have anything else. Yeah.
Thank you.
Yeah. So if there are no other questions, we can end today and meet on Thursday. I think you will get a notification from NPTEL with the exact time. Okay. Bye.
Okay. Bye.
Yeah, thank you.
Bye.